The dimension of a vector space is the number of vectors in any basis for it. And it's the number of linearly independent vectors required to span the entire space. If we're in Rn, then the dimension is obviously n. These basis vectors are written like this, where you have 1, 0, 0, 0, dot, dot, dot. And this is assuming it's a nearly infinite or even infinite dimensional. So for 2-dimension, 3-dimension, 4-dimension, 5-dimension, etc., these basis vectors are just 1, 0, 0, 0, or 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, etc. For matrices, it's a little more complicated. I guess you use the rank theorem. And this is the rank of A plus the dimensions of the null space, and that equals n. This is number pivot columns, number non-pivot, and this is total columns. This would be dimension of row space. Null space dimension. And then this is the dimension of the input space. What this means is if we have a matrix M by N, the N here is the input space, and the M is the output space. This means that it takes these N vectors as output, or as input, sorry, and these M vectors are output. For example, if we had a 3x2 matrix, this has 2 columns and 3 rows. This matrix will map from R2 to R3. If you were to multiply by some vector, something like that, and you multiply the matrix by that, you get another vector, a 3-dimensional vector. Matrices represent a linear transformation. So it also could be like a change of basis, but in this instance it's a linear transformation. We're mapping from R2 because we have 2 dimensions, but 3 3 rows, 2 columns. We multiply by a 2-dimensional vector, and we get a 3-dimensional vector. If we were to do a 2 by 2 matrix, let's say we have A equal 1, 2, 3, 4. The first thing we're going to do, if we want to find the dimension of this with the rank theorem, the first thing you do is you row reduce, and row reducing will give the identity matrix. So basically we're going to have 2 vectors, 1, 0, 0, 1. If you were to solve AX equal 0, 0, or the 0 vector, do you only get the trivial solution? And the answer is yes, you would only get the trivial solution, which would mean that X would be the 0 vector, so that the dimension of the null space is 0. And we have 2 pivot columns here and here, so that we have 2 pivot plus 0 non-pivot, and that's equal to 2, which is a number of columns. Since the columns of this are linearly independent, and there are 2 in R2, they span all of R2. But for matrices, the dimension of the entire matrix is m by n, and for a 2 by 2 that would be 2 times 2, which would be 4 dimensions. So this entire matrix is a 4 by 4 dimensional object. As a linear transformation, this matrix maps from R2 to R2. It just changes the well, this matrix wouldn't change all that much. The identity matrix wouldn't change all that much, but the original matrix might change things quite a bit. But because there are 4 entries, the entire matrix itself is 4-dimensional. Anyway, thanks for watching. I think that's pretty much it. Also, the dimension of polynomial spaces. Polynomials going x, 1x, x squared, x cubed, ... all the way to the x to the n. This dimension is n plus 1. Because this is the basis. And if you're a secondary polynomial, you're x squared plus x plus 1, and that would be 3-dimensional. Function space, apparently, I guess, is really tricky and complicated, and I don't understand that very much. But yeah, matrices are m by n, and these include vectors also. So m by n meaning we multiply them. So like a 3 by 3 matrix would be 9-dimensional.